Hello students, I am Dr. Rajaram Dhok from Savitribai Phule Pune University affiliated Agricultural Development Trust Shardabai Pawar Mahila College Shardanagar Baramati. Let's start. Today we learn about the Sidgwick model, or that Sidgwick model is also called as effective atomic number. So this Sidgwick model is explained by the scientist Sidgwick. So that Sidgwick scientist interpreted the Werner's coordination theory in terms of the electronic theory of valency. So Sidgwick have not explained some new model, but he have used the Werner's theory, and Werner's model, he interpreted into the electronic theory or valency theory, and he given the name, its own name, that is the Sidgwick model. So this Sidgwick extended the Lewis theory to the bonding in coordination compound. This model has based on the different points or different postulates, so that Sidgwick have explained Werner's primary valency is the electrovalency. Means Werner's primary valency is the positive valency, and he given the name, that is the electrovalency. For example, chromium plus 3 ion in chromium chloride. So in chromium chloride, chromium carries plus 3 charge, and it arises due to the loss of electrons from metal atom. And he explained that theory as a electrovalency. Then he also explained in their model that secondary valency is the coordinate valency. Means that is the electron pair sharing, and he suggested ligand acts as donor and metal ion accept the electron pair from that ligand. So in this type of valency, a formation of coordination bond takes place between central metal ion and ligand, and in that this bond is transferred from ligand to metal, so that is called as ligand to metal bond. So this ligand to metal bond we can show, that is pointed arrow from ligand to metal. So according to the Sidgwick idea, structure of the complex. So if we take the example NiNH3 6 2 plus. So here we write NiNH3 6 2 plus. So this type of structure that can be shown by the way. So here nickel is at the center and 6NH3 is attached at the 6 corners of octahedron. So when these are attached, then at that time there is ligand donates their electron to metal, and from that he explained their theory or Sidgwick concept of effective atomic number. So this Sidgwick scientist introduced this concept of effective atomic number, and in this he explained that the tendency of different metal ions to form stable complexes is observed. Means when we take any coordinate complex, then that coordinate complex is formed, and in that stable electronic configuration is formed, and that is usually identical with that of the some inert gases. So simply he explained that coordinate complex contains metal, ligand, and that all are stable, or total number of electrons with that all constituents means metal, ligand, and any other which is present in that, that is equal to the inert gas. And when that is equal to the inert gas, then it acquires certain stability. And when it acquires certain stability, then he explained that EAN rule is obeyed. And so that Sidgwick have explained this in the form of their theory, in the form of their postulates. And he explained what is EAN. And for that, Sidgwick have given the definition for that. So total number of electrons associated with the central metal ion in a complex means that is the number of electrons of metal ion plus electrons donated by the ligand, that is called as effective atomic number. Means in any coordinate complexes, total number of electrons of metal and electron taken from the ligand, its total is, if equal to the inert gas, then that is called as effective atomic number. And if it is equal to inert gas, then it obeys their theory. And if it is not equal to inert gas, then it not obeys Sidgwick theory. So that inert gas number may be 36, 54, 86, it depending upon the which metal and how many electrons present in that. So this Sidgwick showed that for metal ions, the effective atomic number is the same as the atomic number of next inert gas. So in some cases, for example, chromium plus 3, nickel plus 2, Fe plus 3, it may be 1 or 2 units less or more. And in that case, there is confusion that EN rule is obeyed or not. And for that purpose, here we see the different examples, and from that you get idea about this rule. So these exceptions of that EN rule is also observed, but also these complexes are stable complexes. But according to the Sidgwick model, these are not a rule. And so this theory is limitations, or this theory has only little importance because it is not universally used, because there are so many complexes which has not obeys EN rule, but also they are stable. And so this theory is not uniformly used, or they have certain limitations. And so for calculation of the EAN, there is simple formula. So that formula is EAN is equal to Z minus N plus 2 into coordination number. So here Z means the atomic number of the metal. Means if we take the iron, then atomic number 26, nickel atomic number 28, like that. Z value means that is atomic number of metal. N means number of electrons lost in cation formation. Means how many electrons are lost in ion formation or cation formation, that is the small n. And Cn means coordination number. So by using this formula, means simply we take the atomic number of metal, then subtract how many electrons are lost from that. Then we see what is the coordination number, multiply by that coordination number by 2, and then add in the total electrons of metal, and that is the EAN. So here we see the different examples, and from that example you get idea that EAN rule is obeyed or not obeyed. So we take first example Fe 3 minus. So we solve these examples by taking the formula EAN is equal to Z minus N plus 2 into coordination number. So Fe has atomic number 26. In this example, there are 6 Cn ions and charge on the complex ion is minus 3. So oxidation number of Fe is plus 3. So Fe has oxidation number plus 3, meaning of that Fe loses 3 electrons. And so we can solve here 26 minus 3 plus here coordination number is 6. So 2 into 6. So simply we solve that 26 minus 3, 23, 2 into 6, 12. So we solve 23 plus 12, that is 35. So this 35 value is near to 36, that is the electronic configuration of krypton, but it is not equal to electronic configuration of krypton. And so we write here 35 is not equivalent to 36. So according to the Sidgwick theory, here this Fe 3 minus does not obey EAN rule, or it is not stable according to the Sidgwick model. So you have asked the question, solve the problems, or it obeys EAN rule or not, or calculate the effective atomic number. So you simply calculate by this formula EAN is equal to Z minus N plus 2 into coordination number. Again, we see some other examples. Second example. Here we take the NiCO4. Here nickel has atomic number 28. Here carbonyl is the neutral ligand. So there are 4 carbonyl, but they have not any charge. They have not any oxidation number. So oxidation number of nickel in this example is 0. So nickel not loses any electron. So we write 28 minus 0. Then coordination number is 4. So 2 into 4, that is the 8. So 28 plus 8, 36. So this 36 means it is equivalent to the electronic configuration of krypton. So we say that this NiCO4 obeys EAN rule. Means according to the Sidgwick, this compound is stable compound and it obeys effective atomic number rule. Now we see one other example, PtNH3 2 plus. Here platinum has atomic number 78. In this example, oxidation number of platinum is 2 plus. So 78 minus 2. Then coordination number is 4. So 2 into 4, 8. Then we solve 76 plus 8, 84. But inert gas near to 84 is 36, that is radon electronic configuration. So this 84 is not equal to the inert gas radon. And so according to the Sidgwick, this PtNH3 2 plus does not obey EAN rule. Or for this example, effective atomic number calculated is 84. Now again we take some examples. So here I have given you table, and in that table different examples, atomic number 26, 27, 28, then 29, chromium, platinum, these are given. So in that there is example Fe 4 minus, COCN NH3 3 plus, NiCO4, PT 4 plus, Fe 3 minus, CrCO6. So these are the some examples. So you solve this all the examples by using that same formula, that Z minus N plus 2 into coordination number. So by solving this, we get here EAN 36, 36, 36, 86, 36, 36. So these all examples are examples of complexes which obeys EAN rule. Now this table 2 is for the complexes which not obeys EAN rule. So here in Fe we have taken here efficiency 4 minus, means this is the K3 efficiency. So K3 efficiency has EAN 35, but K4 efficiency has EAN 36, means these both the compounds are stable. These compounds are the good reagents we use in the laboratory. But according to the Sidgwick, one is stable, one is obeys EAN and other not obeys EAN. So this is one drawback of these theories, or this is one limitation of these theories. So see, by solving this, we get here value 35 for the Fe, then 38 for nickel, for platinum 84, for chromium 33. Means here EAN rule is not obeyed. So simply, according to the EAN rule or Sidgwick model, these examples, these complexes are not stable complexes. But actually these are the stable complexes. So there are some limitations of this theory. Now we see the limitations. So already we have seen that limitations in that examples. So in the so many examples from the table 2, we observe that EAN rule cannot be uniformly applied to all complexes. Means there are many exceptions. They are not obey EAN rule, but they are stable. And so this rule is not uniformly used. Then ligands donates electron pairs. Metal ion accepts them. Due to this, it appears that there is an accumulation of negative charge on the metal ion. And this decreases the stability of complex. Because according to that, ligand donates electron and metal accept electron. So we know that the species which donates electron, that is carries positive charge, and species which accept electron, that carries negative charge. So according to the Sidgwick model, metal carries negative charge, but we know that generally metals are positively charged. And so this is one limitations to the Sidgwick model. Then 2s electron pairs in ammonia H2O have not any bonding characteristic. And so how that it donates electron? In many complexes such as fluoro or other bonds between the central atom and ligands, they are not covalent, but dominantly they are ionic. And in that case, how that ligand donates electron to metal? So there is some objections. So it gives no accounts of geometries of any complex. Means that Sidgwick model only explains that how many number of electrons present, total number of electrons present, but there is not explained any geometrical shape of that complex. And so this theory has so many limitations. It is simple, but they have limitations. So this theory shows some merits because it is easy to understand. We can easily explain how many electrons present in that, or it obeys EN rule or not. And so simply you can explain. So merits are simple or merits are good because it is easy. But easy means not correct. And so instead of the merits, they have so many demerits. So we have to consider that for a limited purpose and not uniformly we use this theory.